Okay, so we're doing trigonometry. My Bluetooth's not working, so I'll stay more here where the microphone is. Trigonometry is the measure of triangles, right? The metry part is measure of, right? Originated in the 3rd century BC when astronomers noted fixed ratio of sides of similar right triangles, right? You know what that means, right? Similar right triangles? What does that mean? Say again? In a proportion, right? A triangle that has the same angles and the sides are proportional to each other. So it's the same shape, but maybe a different size. So they notice that kind of thing. You know, trigonometric functions are what you call periodic. And the basic one that we look at is y equals the sine of x. And that is a picture of y equals sine x just done on the calculator right there. What do you notice about the shape of it? How would you describe it if you had to describe it to somebody? It's kind of a wave, right? It's often called a sine wave, right? So what kind of things could you model with a sine wave? Sound, okay, sound could be. Sound is like a longitudinal wave, but what else could you model with a wave? How about a wave? Could be. How about a wave? How about if you're interested in the ocean and you're interested in the waves in the ocean? That might be helpful. What if you're like me? I was a meteorologist and you wanted to model temperature, and temperature goes up and it goes down and it goes up and it goes down. And you know that it's going to do that forever, right? So you can't just use, you guys done? Okay. You can't just use, for example, like a quartic. Well, that'll go up and down, you know, how many times, or I'll make it a 6 degree or whatever, right? We need it to go on forever. And that's what a trig function does. And that's what a sine function particularly gives you, that kind of wave kind of feature right there. Now, I had, over the break, because my wife is always offering my help to people that I don't even know. And she, so somebody that she works with, his brother, I think he works at Ferguson, and he has this belt contraption. I don't really even understand what they're trying to do with this, except for that he's taken a belt and he's cut it in 2 halves, and they put this strap, the brown piece in the middle there, which is like elastic. And then the white square is where they're measuring. And they're measuring like if you have this around your waist, and when you breathe in and it gets tighter, then the capacitance, that's a unit of something, you know, goes up. And when you breathe out and the belt relaxes, it goes down. And so he got himself a graph, and he didn't know what to do with it. And so she, you know, again, offered up my help, and she got that. And I mean, the first thing I'm thinking is, well, it kind of looks like a sine wave. You know, I mean, it's going up and it's going down, and it looks like it's going on forever. So you can kind of see what's going on. I mean, the scale on the bottom goes from 0 to 1800. But, you know, these are not in units of seconds or minutes. It's actually, that is 1 minute long. And you could see like that every time that goes up to the top, that's like taking a breath in. And then it goes down to the bottom, that's like breathing out. So up and down and up and down. And I think you counted them up, there was 18 breaths or something like that. Does that sound right? That in a minute you might breathe in and out 18 times. So anyways, he didn't know what he could use to model this. So I said, why don't you use a sine equation? And I not only did that, I said, okay, take the sine equation and then do the kind of things that we did where you would transform it. Like this thing is actually up, the scale on the left there is like it's up about 3,100. So I would want a vertical shift up 3,100, right? It looks like, in a detail that we wouldn't know yet, it looks like it's been shifted a little bit to the right. Okay, I know how to do that. I subtract something inside the function, right? How high it goes up and down, that's something you do with a stretch or a shrink. So all those kind of things I could give him. And then he came back with, well, what he really wants to study is, you can kind of see the overall waves there. But if you look even closer at it, this is just one wave. And you see that there's actually a whole lot of other little bumps in there. And so he really wants to get at, okay, I can see the big thing. I know that's the breathing in and out, but is there something else going on? And so ultimately what he's going to do with this is do a regression equation, something that we could have done with our own calculator, right? Stat edit, L1 and L2, and then that is an option that we didn't use yet, but we could. Stat, calc, and I think you go down to like A or B at the bottom, and then you could come up with a sine function. And that would give you the big wave, and then you could like subtract those values from your data, and you would only be left with all those little variations in the wave. That's all you would see if you subtract out the big wave. So he was very happy with that input, but I don't think he's going to give me any part of his pay. So, I mean, part of what I think is interesting about this is a lot of times in math, like the track that everybody's on now, it's kind of referred to as the calculus track. And you get almost in your mind like there's nothing useful in math until you get to calculus. But that's not true. I mean, just didn't take calculus to do this, right? And there's things that we'll do in this unit that are really, really important kind of math things that were done using trigonometry way before there was ever even calculus invented. So, this is pretty powerful stuff. Now, there is now trigonometry on the SOL. Okay, that's not part of our SOL. But when you get to math analysis next year, if that's what you take, definitely the trigonometry makes up the major part of that class, and that is usually the stumbling block. So we really want to cover enough here that you've got a good start on that next year. When I was in high school, this was the typical pattern, right? I mean, I was, let's say in the advanced category, but still, you started in Algebra 1, then you went to Geometry, then you went to Algebra 2 Trig, and then, for people like me, we went right to Calculus. There was not a class in between there. And we didn't have SOLs or anything like that that would divert our attention in the last 9 weeks. Right? We did trigonometry in that last little bit. In fact, as I recall, it was only 6 weeks. And I never needed more trigonometry than that in the rest of my math and science career. And I have degrees in math and science. So, I mean, trigonometry it's very doable. And if you're good at the algebra part of things, then it's not that much of a stretch to just learn a few new functions. Okay. So, don't be intimidated by it, basically. Okay, you can do this stuff. So the way the unit will break down is like this. The first lesson is going to be right triangle trigonometry, much of which you already did. This is what you do in geometry. Remember, first you did Pythagorean theorem, then you did the special right triangles, then you did some trigonometry, a very basic amount. That's mostly what we do here. We'll go into more detail, but it's mostly that subject. The next unit, we do something that's called the unit circle, right? It was where we introduced radian measure, which Matt was asking about. And then after that, we do law of sines and law of cosines. So the law of sines and cosines is what you use when you don't have a right triangle. So we can solve everything about right triangles using stuff that we've already done. Law of sines and cosines, now we can deal with triangles that don't necessarily happen to be right triangles. Now if we stay on track here, I would expect that we're going to have our quiz on the 18th and our test on the 24th. That's the plan. Okay, so some of this, again, should be familiar to you because you did this in geometry. Okay. I wonder if that must be what happened. Okay, so right triangle. So it's a right triangle because that little right angle in the 90-degree angle there, that's how we indicate it. We have to label one of the angles, the acute angles, right? So the other two angles must be acute. What does that mean? Less than 90, right? I mean, is there any way for one of those angles to be more than 90? No. Not if this angle is 90, then if you had one other angle that was more than 90, then together they would be more than 180. So that can't be the case. Okay, so usually you mark one of the angles with the Greek letter theta, right? That's how you pronounce it, theta. And sometimes we use different variables, but that's the most common for an angle is theta. Okay, and then we define the three sides with respect to that angle, right? The side which is across from the angle is called the opposite side. The side which is next to the angle is the adjacent side, and then the hypotenuse is always the hypotenuse, right? It's always the angle across from the right angle. And then we define these three trig functions. The sine of theta is the measure of the opposite side divided by the hypotenuse. The cosine is the adjacent side divided by the hypotenuse. And the tangent is the measure of the opposite side divided by the adjacent. So usually we have like mnemonic devices of some kind to help us remember those three definitions. How many remember the SOHCAHTOA? SOHCAHTOA. Okay, did you have any clever way to remember those in order? Garrison?
The math teacher said it was like some will be cop another,
Okay.
One of the calculus teachers.
Okay. I've heard a more Sesame Street ready kind of one. Some old horse caught a horse taking oats away. Or some old horse came a hopping through our alley. I've heard both of those. You could just get it by pronouncing it, SOHCAHTOA, get all those letters. In any case, right, sine, the SOH is because the sine is opposite over hypotenuse, which is what this says right here. The CAH, cosine equals adjacent over hypotenuse. And TOA, tangent is opposite over adjacent. Again, when I was your age, or actually a little older because I took it in 11th grade, we did this one. OAO, HHA. And then we would say Oliver and olive oil have had algebra. And the O over H, you had to remember it was sine. The A over H was the cosine, and the O over A was tangent. So whatever way you remember them, you got to remember those. Okay, now here's the three functions that you didn't learn about already, which are called the reciprocal functions. Cosecant, secant, and cotangent, right? All three of those are just flips of the original three. All you got to remember is, okay, which one is the flip of which one? And to me, like tangent and cotangent, okay, we can be pretty sure those are flips of each other. Now you got to remember, is sine the flip of the secant, or is sine the flip of the cosecant? Is cosine the flip of the cosecant, or is cosine the flip of the secant? In my mind, I'm thinking it ought to be cosine and cosecant because they both start with co, and that's absolutely wrong. So it should be that the sine, the flip of the sine is the cosecant, the flip of the cosine is the secant. And that's why when I write these down, I'm making sure to write them right across from the one that they're a flip of, right? So if the sine is opposite over hypotenuse, the cosecant is hypotenuse over opposite. Just flip the fraction. Okay. Now what's the biggest side in a right triangle? It's always the hypotenuse, right? So the sine of theta, since it's the opposite over the hypotenuse, and the hypotenuse is definitely the biggest side, then you know that the sine of theta has got to be less than 1. Right? It can't be more than 1, because then you'd have the opposite is bigger than the hypotenuse. Same thing for the cosine. So that'll be important later. So the sine and the cosine have to be less than 1. In fact, it turns out they can't equal 1 when we're not necessarily doing right triangle trigonometry. But they definitely cannot be more than 1. Okay. So we good on that? So next. So evaluate the 6 trig functions, those 6 that we just did on the other page, for the angle theta. And you can see that I marked the theta in the bottom right corner. Okay, now, in order to do this, what do I need to fill in on that triangle? You got to know the hypotenuse, okay? How are you going to find the hypotenuse if you know the other 2 sides? Pythagorean theorem, right? So it's got to start by doing that, right? The square root of 5 squared plus 12 squared, which is 13. You know, when you get those three values and they're all integers, that's called Pythagorean triples. And you know, they're 3, 4, 5, 6, 8, 10, 5, 12, 13. There's, you know, infinitely many of these things. Okay, so now sine of theta, according to what we said on the last page, should be opposite over hypotenuse. So what is that? 5 over 13. How about cosine of theta? Yeah, don't turn them into decimals, just say 12 over 13. How about tangent? Opposite over adjacent. 5 over 12. Now notice one thing there, right? If the sine is 5 over 13 and the cosine is 12 over 13, the tangent is 5 over 12. Tangent is actually sine divided by cosine. Right? If I divide 5 over 13 by 12 over 13, the over 13s cancel and you just get 5 over 12. So that is a truism, right? That the tangent equals sine over cosine. Okay, now the reciprocal functions, I wrote those to the side right across from the original 3 for which one it was a flip of, right? So now I can just fill this in, right? 13 over 5. 13 over 12, and 12 over 5. Okay. So try to do that one. Same deal. Right? You know the hypotenuse and you don't know one of the legs, so the math is going to be the square root of 17 squared minus 15 squared, which is 8. Okay, now the angle is moved, but everything is with respect to the angle as it's marked. You know, what's the opposite side in this triangle? Right, the opposite was the 15, and the hypotenuse is 17. Right, the cosine adjacent 8 over 15 over 17. Right, the tangent 15 over 8. And then we flip them all. Right, 17 over 15 and 17 over 8 and 8 over 15. Okay, here's the next kind of question, right? If theta is an acute angle of a right triangle, and the sine of theta equals 4/7, what is the tangent of theta? Okay, so first thing we need to do is draw a triangle, right? Let's look at the triangle. There's my right triangle. Kind of sloppy, but you can, either one of the acute angles, just make sure you mark it. And let me erase that little piece right there. Now we need, if the sine of theta is 4/7, then it should be the opposite is 4, the hypotenuse is 7. Okay, now we need to use Pythagorean theorem. What is this side right here? And don't turn them into decimals, right? This needs to be simplified square roots if it's simplifiable. So what should it be? The square root of 7 squared minus 4 squared, which is the square root of 33. So don't turn it into decimal, just leave it like that. Okay, now we know all three sides. What is the tangent of theta? Right, should be opposite over adjacent. So what is that? 4 over the square root of 33. But now, we shouldn't leave the square root in the denominator. How do we rationalize the denominator? Multiply by the square root of 33 over the square root of 33, right? Which is 4 times the square root of 33 divided by 33. Usually the way that a question like this might be worded is it might say, find the exact value. Okay, by exact, it means you're expected to have a square root in there. If you turn it into a decimal and write it down, it's not exact anymore. So if it says exact, then definitely you want to, rationalize denominator, simplify the square root as much as you can, but you're probably going to have a square root in the answer. Okay. So try that one. Right? Theta is the acute angle of a right triangle. Cosine of theta is 7/10. What is the sine of theta? So draw a triangle. Mark an angle as theta. Cosine is 7/10. Adjacent over hypotenuse. Right? Find the value of the third side. Square root of 10 squared minus 7 squared, which is the square root of 51. So what is the value of the sine? Right? Opposite over hypotenuse. Over 10. Any questions about that? Okay. Now, I'll kind of present this in the order that the book has it, and to me, I'm not sure this is like the greatest place. We're going to end up referring to these slides later on anyways, but I'll do it anyways. I mean, this is using the special right triangles that you already used in geometry, right? This is the 45, 45, 90. We can tell what is the sine of 45, all 6 trig functions of 45-degree angles, right? Because that's the only acute angle in a 45, 45, 90 is only 45. So again, if it doesn't matter which one I'm looking at. Let's say I'm looking at this one is my 45 degrees, right? The opposite over hypotenuse would be x over x root 2. And because x is a common factor in the numerator and denominator, it cancels, and all you're left with is 1 over the square root of 2. Right? Now, 1 over the square root of 2, we rationalize the denominator, and you get square root of 2 over 2. So notice we didn't know what the size of what x is. So we really don't know the size of this triangle, but it doesn't matter. Right? Just like they noticed in the 3rd century BC, it was the similar ratios, or the ratio of sides for similar triangles. They don't have to be the same size. They just have to have the same angles. Right? Now, when you flip the sign to get the cosecant, right, if you try to flip root 2 over 2, then you've got 2 over root 2. And then you've got to rationalize the denominator again. Probably better to just flip it when it was 1 over the square root of 2. Because when you flip that now it's just the square root of 2. There is no denominator except for 1. Right? Cosine of 45 degrees, same calculation. It's still x over x root 2, which gives us root 2 over 2. The secant should be the flip of that root 2. The tangent of 45 degrees, right? Opposite over adjacent, which is x over x, which is 1. And the flip of 1 is 1. So we know what the sines, we know all 6 trig functions for 45 degrees. Right, what was the other special right triangle? 30, 60, 90, right? And 30, 60, 90 had its own formulas, right? So remember, across from the 30 degrees, that was x. Or you might have done it where they said n. Sometimes you use n, sometimes you use x. Right? The hypotenuse is always twice that, 2x. And across from the 60 degrees, x times the square root of 3. Those are the formulas for the 3 sides. So now we can find sines in all 6 trig functions now for 30 and 60 degree angles. Right? the sine of 30 degrees should have been opposite over hypotenuse. That's x over 2x, which is 1/2. So the sine of 30 degrees is 1/2. The cosine of 30 degrees should be x root 3 over 2x, which is the square root of 3 over 2. Right? The tangent should be x over x root 3. The x's cancel, and 1 over the square root of 3, you rationalize the denominator, root 3 over 3. Right? And then you flip. Right? The flip of the sine, 1/2, is the cosecant, 2. Right? The flip of the cosine, root 3 over 2, is 2 root 3 over 3. And the flip of the tangent, again, I would flip this 1 over the square root of 3, and I get root 3. Okay, now when it comes to the 60 degrees, right, they're just changing the reference angle in the triangle. So now we're going opposite with respect to the 60 degrees would be x root 3. And it's still divided by 2x. So the sine of 60 degrees is root 3 over 2, which is the same as the cosine of 30 degrees. And that'll always be the case because of the way these things are calculated. Right? The sine of one acute angle is equals the cosine of the other acute angle. And vice versa, right? The cosine of 60 degrees now is 1/2. That was the sine of 30 degrees. Okay? The tangent of 60 degrees is the same as the cotangent of 30 degrees, root 3. And then you can see the cosecant and the secant. So now we know sines, cosines, and tangents for 30, 45, 60 degrees. And we'll refer back to these values in a little bit. How many of you remember these formulas for the sides? Because if you know these formulas, across from the 30 is the x, across from the right angle is the 2x, the other one's x root 3, or the similar ones for 45, 45, 90. That means you don't have to remember all this stuff on this slide here. I mean, you could put it together anytime you want. Don't memorize it like it's a bunch of disconnected information. It actually connects to things that we've done before. Okay. So, it seems like I skipped something there. Okay, maybe not. Find the value of x. Okay, well, you could solve this problem in geometry without using trigonometry. But we'll use the trigonometry to do it. Okay. Which trig function would we use since the 30 degrees is where it is, and these are the two sides that we're looking at? Would that be sine, cosine, or tangent? It's a cosine, right? Adjacent over hypotenuse. So we should say that the cosine of 30 degrees equals x over 8. Okay, but from the previous slide, what's the cosine of 30 degrees? Just look. What was the cosine of 30? Is root 3 over 2. So root 3 over 2 is x over 8. Solve for x. Multiply times 8. Four times the square root of 3. If you were doing this like you did in geometry, you would have said, oh, this 8, this one side that we know, I can set, let me change color. I could have set that equal to the 2x. And then I say, okay, well, if that's 2x, then x must be 4. And then this one should have been 4 times the square root of 3. So without trigonometry, you could have done it like you did in geometry. Okay, so try that one. See if you use trigonometry to figure out angle A, side A, and side B. And not drawn to scale. How's that? So let's say I'm going to find A, and I'm using this as the reference angle. Then which trig function would I use? If I'm trying to find the A, the sine, right? It's opposite, and I know the one side that I know is the C, the 5. And I got to use the one side that I know. So sine of 45 equals A over 5. Okay, well, what did we say was the sine of 45 degrees? The square root of 2 over 2, right? So it equals A over 5. Okay, so solve for A. A equals 5 times the square root of 2 over 2. Okay, so let's go ahead. That was wrong. So when you're dealing with right triangles, sometimes the problems, they're going to say like solve the triangle. And by solve the triangle, it's like find the missing sides and angles. Find all of them that you don't have. And there's a convention for how we label triangles, which goes like this. Use capital letters A, B, and C for the vertices, and always use C for the right angle. So, and the other two don't matter, A and B. And then for the sides, use lowercase letters. And across from the capital A, that's where the lowercase a goes. Across from the capital B, that's the lowercase b. And across from the capital C, that's the lowercase c. So we'll be using these even when we get into law of sines, law of cosines. Okay, people are good. There we go. So solve triangle ABC. Find all the missing sides and angles. Okay, let's see. So the angle is there. The one side that I know is this B right here. So I'm going to have to find either the A or the C. And that'll make a difference in which trig function we use. What if we're going to find C first? Which trig function would I be using if I'm finding C? It's adjacent over hypotenuse, cosine. So we're going to have to set this up as cosine of 28 degrees equals 15 over C. Solve for C. How do I solve that for C? You divide both sides by cosine of 28. I mean, you will. Probably the best thing, if you're going to like solve this step-by-step algebra, multiply times C, right? Then the C is up here. And then divide by the cosine of 28. In any case, this is what it's going to look like. C equals 15 divided by the cosine of 28. Right, degrees. Now, we have way too much trouble sometimes solving that exact kind of equation when the variable's in the denominator like that. So just notice what happened, right? You just swap the positions of these two, right? The cosine of 28 goes to the denominator, the C goes up on the other side to the numerator. I mean, in the end, that is what you're going to get. So if you're having trouble with the algebra, just swap those two. That's what you want to do. Okay, now we go to the calculator, right? Now, your calculators may have been used already to do this. If you want to like go from scratch, you can clear the memory, second plus 712. And let's put in the calculator 15 divided by the cosine of 28 degrees. 15 divided by the cosine, cos, 28 degrees, right? Now, when I hit enter, I'm getting something crazy here, right? Negative 15.6? That doesn't seem right. And it's not. Because actually the calculator is not in degree measure. And when you use the calculator and you mean to put angles in degrees, you got two options, right? One of them, I almost recommend this one, even though I haven't usually used this myself, is you could always do this. Right? You can go 15 divided by the cosine of 28, and then you see where the apps key is? Right there, it's like second column, third row down, purple. Then you go, above that it says angle. So second, apps, and the very first option gives you a chance to put a degree symbol on that. Okay, and enter. So that looks more like it. Looks like it's more like about 17.0. Okay, the other way you can do this, which is usually what we say, is that go to the mode key, right? The mode is just to the right of second, and look down in the third line, and you could see degree off to the right. You know, what you notice about that is there is another way to measure angles, and it's not degrees, that's radian measure, which we do next time. And it's actually the default. Most of the time when you pick up your calculator, it's going to be in radian measure. And when you do the math and you get crazy answers like negative 15 for a side length, you got to be saying to yourself, there's something wrong here. Many, many questions are missed, or at least partial credit, because you're in the wrong mode. Right? Now, if you just get in the habit of every time you do one you want in degrees, then just go second angle 1, you know, and put the degree symbol on there, and then you can let it be in whatever mode that it is. So. Okay, that gives us one of these sides, right? We just said this one is 17.0. Okay, we still have to find side A, and we have to find angle B. How can I find side A? Yeah, I mean, once you know two of the three sides, you could really just use Pythagorean theorem. You don't need trigonometry to find that, right? So A is going to be the square root of 17 squared minus 15 squared. So second quit. So second square root 17, no, actually I was going to say second answer squared minus 15 squared. And I'll get 7.9, so 8. Okay, and then we got to find angle B. What's angle B? Yeah, I mean subtract from 180 or subtract the 2 from the 90, right? So 62 degrees. So just make sure you know what mode you're in when you start doing trig functions of angles. Okay, so try this one. And so go ahead and try that. So what's the angle B? Right, we don't need trigonometry for that. And then you got to find either B or C. Which one do you think would be easier? Find B. So how did you set that up? Tan 32. Sorry, that was wrong. Where's my eraser? Tan of 32 degrees equals 10 over B. Okay, but again, if there's any issues with solving for that B because it's in the denominator, you know, honestly, you could use the 58 degree angle, right? With respect to the 58 degree angle, I would be finding the tangent of 58 degrees, that's not a good degrees, equals B over 10. And now that's easier to solve. Sorry, anyway, I mean, you've got many options for doing this. If I solve it this way, it's B equals 10 over the tan of 32 degrees. Right, and that one, I come over here. 10 divide by tan 32. I don't think I changed my mode, so let me go second apps 1. I get 16.00. And then I got to find, that'll be my 16. And then I got to find the C, right? Pythagorean theorem time. So C equals the square root of 10 squared plus 16 squared. $18.86, call it 18.9. Okay, so we solved it. We found all the missing sides and angles. Okay, here's our real world problem, right? Standing at the Yavapai point near the Grand Canyon, you measure an angle of 90 degrees, marked right there, between Point Powell and Woodforest Point, as shown. Then you walk from this point to this point, and you measure that angle, and it looks like that one is 76 degrees, so I can mark that. Right there is 76 degrees. Okay. The distance from Yavapai Point and Powell Point is 2 miles, right? That's a 2. So how wide is the Grand Canyon between the Yavapai and Woodforest points? Meaning, what is this distance right there? I'll call that x. Which trig function are we going to end up using? Tan, right? Because look at, we got, there's the angle, I'll call it a reference angle, right? Opposite, adjacent. So that would be tangent. Let me change color so I can see it. Tangent of 76 equals x over 2. So x should equal 2 times the tan of 76 degrees. Right? Number crunch that one. Second, or 2 times tan of 76. Second, apps 1. 8.02. So it's about 8 miles. Now, when we get to law of sines and cosines, right, there you can use triangles that are not right triangles. And in fact, that is kind of how most of the early maps of like all of Europe were made, by doing this exact kind of process. You know, where you could like find 2 points and then, you know, figure out the angle to that other point, and then just knowing that one distance between your 2 points, you'd be able to figure out how far away that other point was. And then once you knew that one, then you could do the same thing, like take these 2 points and find another one over here, and then just keep going and going and going. Those were the maps that were used to like within the last 100 years, and they were pretty accurate. You know, we came up with better technology to find them, but it was pretty much this process that they used. Oops. Okay, here's a couple terms that you need to know what they are. Angle of elevation and angle of depression. Right? The key point here is that angle of elevation and angle of depression, they're both angles with a horizontal line. Right? So if I'm looking at this angle here, right? And let's say somebody's on the ground and they're looking up to the top of, I don't know if that's Empire State Building, might be, right? Then the angle of elevation is like how much are they having to like raise their eyes to see the top of that building. Okay. Now, if you were instead on the top of the building looking down to something on the ground, then the angle of depression, right? Again, it's with a horizontal line, right? With that line. With that line. I mean, that's the main thing you got to get right. Because mostly in a word problem, it's not going to be drawn for you. It's going to be just like describing, okay, the angle of depression is, and then you got to draw your triangle and label it correctly. If you start labeling like this angle right there, then you're kind of completely missing the point of angle of elevation, angle of depression. Okay, so let's look at right. A parasailer is attached to a boat with a rope 300 feet long. The angle of elevation from the boat to the parasailer is 48 degrees. Estimate the parasailer's height above the boat. Okay, so with respect to that 48 degree angle, which two sides do we have? Opposite, adjacent, hypotenuse. Which two out of the three? Opposite and hypotenuse. So which trig function are we going to use? Sine. So we're going to say the sine of 48 degrees equals h over 300. Right? Solve for h. H equals 300 times the sine of 48 degrees. So 300 times the sine of 48, and make sure you got the right mode for your angle. That looks like 222.9 is the height. 222.9 feet. Okay. Oh, I'm going to skip over this one because I tried to change the. No, I'm going to just fix it on the spot because you could see up in the problem I actually changed this to 38 so that it's not the same problem, and I said let's not find the h, let's find black. This is 38 degrees, and let's find this distance right there. So what trig function did you use? Cosine. Cosine of 38 degrees equals d over 300. So d equals 300 times the cosine of 38 degrees. 300 times cosine 38. Second apps 1. 236.4. Feet. Okay, change to blue. Okay, I think I'm ready for... Okay, so the one thing that we've been solving for missing sides, but we haven't been solving for missing angles yet. And that is something that you did in geometry. But you may not have had as much of an explanation for why you did it the way you did it. So we're going to go a little more into it, and you'll see how this goes. But in order to solve for missing angles, you use inverse functions, something that you would not have known about in geometry at that time. But, you know, just look at the calculator. What do you see above the sine and the cosine and the tangent? The inverse sine and the inverse cosine and the inverse tangent. So, you know, they're there. Remember that for an inverse function, they undo each other, right? A function and its inverse, they undo each other. If f of 1 equals 2, then f minus 1 of 2 equals 1, right? They point in opposite directions. And when you take the composition of a function and its inverse, they should cancel each other out, and then you just get x left. So it's a way of isolating the variable that's inside of a inverse function, or inside of a function. Okay, so let's see. Let's go to first we're going to look at 30, 60, 90, and 45, 45, 90. I keep hitting the wrong thing. So again, if if we want to know what the cosine inverse of root 3 over 2 is, then what we're saying is that, you know what, for some angle theta, cosine must equal the square root of 3 over 2. So go back to that slide where we had, the special right triangles. What was the angle that had a cosine equal to root 3 over 2? Right? It was 30 degrees. Therefore, the cosine inverse of root 3 over 2 is 30. Right? If you go back to that slide, you'll see that the cosine of 30 degrees is root 3 over 2. Right? Therefore, the cosine inverse of root 3 over 2 is 30. They just got to go in opposite ways. Okay. Was there any angle that we saw so far that had a sine that was equal to 2? I mean, what did we say about the size of the sine? What was like the limiting value for the sine? Is 1, right? Because if it's opposite over hypotenuse, the hypotenuse is always bigger. So just for grins, make sure that you're in the right mode, right? Mode, degree, and let's take the sine inverse of 2, right? Second, sine inverse of 2. And what you find is it's an error. It's a domain error because, again, sine cannot be more than 1. So when you get that kind of thing, that's why. Sine could never equal 2 because the ratio of sides could never be more than 1. So you just say undefined. Shouldn't do that. I should do like this. I should say that sine of theta is less than or equal to 1. Okay, try those two. Those two definitely had values if you look back to those slides. Okay, so at what angle did the sine equal root 2 over 2? So 45 degrees, right? Again, that means that the sine of 45 equals root 2 over 2. Right? At what angle did the cosine equal 1/2? Okay, 60 degrees. Right? That is because the cosine of 60 degrees equals 1/2. Okay. Next. Okay, that's going. Okay, what is the measure of the angle in this triangle? Okay, what is the trig function that we should use? Cosine, right? Because it's got, looks like with respect to that theta, we've got adjacent and we've got hypotenuse. So we definitely want to set it up like this, right? Cosine of theta equals 6 over 11. Okay, now you got to solve for the theta, which is inside the trig function, right? You can't divide by the letters COS, right? It doesn't work that way. What you can do is you can take the cosine inverse of both sides, right? So if I take the cosine inverse of that side, what I've created on the left here is a composition of a function and its inverse. And what does that equal? When you take a composition of a function and its inverse, you just get the theta. The cosine inverse and the cosine cancel each other out. Remember? And so now all we need to do is, use the calculator. What is the cosine inverse of 6 over 11? 76.9? 56.9? 56.9 degrees, does that sound right? Okay. So now in geometry, when you solve these, and you did, you probably just went right to this right here, right? you wouldn't have known anything about inverse functions, how the composition of a function and its inverse cancel each other out, right? So you couldn't have done that. And you don't have to show that like every time you solve it now, but that is where it comes from. That is why we do that. Okay, so try that one. See if you can find the theta in that problem. So what trig function did you use? The sine of theta equals 8 over 12. Therefore, theta equals sine inverse of 8 over 12. Theta equals $41.8. Okay, and last slide. Again, I had to make this one up. A monster truck drives off a ramp in order to jump onto a row of cars. The ramp has a height of 8 feet and a horizontal length of 20 feet. What is the angle of the ramp? So which trig function does it look like we're going to use? It looks like we've got opposite and adjacent. That's tangent. So tangent of theta is 8 over 20. So theta is tan inverse of 8 over 20. $21.8. So that was that. So the two slides, the 2 pages for the homework, the first one has got all the missing sides, but it doesn't have any missing angles. And the second one has got the missing angles. They've got this split up kind of funny ways. So that's why we're doing it, jumping around a little bit.